All right, any questions? Sounds like the lab went okay yesterday. Abby did mention that, so there's a bug in the the program where sometimes the data will save, but it's just an empty file. So it saves a file, but if you don't actually check and open the file to make sure there's data in it, you can think that you have data, but you don't. So from now on, instead of just checking that you have a file saved, check that it actually has data in it as well. And if you ended up with an empty file from your lab yesterday, just email Abby and she'll get you sorted out. Yes?
I saw the due date was the 22nd. Is
That's
that
correct.
just for the people who had it 2 weeks prior to the 22nd? So those of us who have it at a later date, we will have it due 2 weeks later? Because it'd be kind of...
Yeah, so the thought was 2 weeks is plenty of time to do a lab report, and you can sign up for the time that you want to sign up for. And so whenever no matter whenever you take the data, it's still due on the 22nd. I mean, I feel like 2 weeks is plenty of time to do it.
But those of us who don't get 2 weeks, that's still enough?
Yeah, I mean, 2 weeks minus 2 days, right? Yeah.
Substantial enough?
Yeah.
Okay.
Yeah, I feel like that's a substantial amount of time. Yeah, just put it in the Dropbox. Sorry. Yeah. I feel like it's an adequate amount of time to do the lab. Yeah. I mean, we just have to spread it out over a couple of days by nature of how many students are in there. Okay, any other questions? Homework? Yeah, just go put it in the Dropbox. Because of the fire alarm, Shin's going to pick it up at the end of class. Okay, let's get started talking about fins again. So we left off mentioning that we use fins to enhance heat transfer by convection. So if we look at the convection rate equation, there are a couple of ways we can enhance heat transfer. Increasing H, increasing the surface area, or increasing the delta T. And there is typically some kind of more significant cost associated with increasing H. So that would be due to, you can increase H by increasing the flow speed over the fins, and increase delta T by cooling the external fluid more, which would also be more costly than just changing the geometry of the surface so that it has an increased surface area. So we'll kind of draw a couple of contrasting cases. So previously we'd just been looking at heat transfer by convection over a plane wall. So if we have just a plain wall with conduction, heat moving through the wall due to conduction. And then we have heat lost from the surface by convection. Some fluid at T infinity and H. And then we have a surface temperature and area. And as I mentioned last time, in a situation like this, we'll have Q conduction being in the same direction as Q convection, so parallel. But if we have a wall with an extended surface, we'll see a couple of different effects. So say we have a rectangular fin in this case. All right, so we've got an extended surface here coming off this wall. So now we have conduction coming through in this direction. And we are typically going to assume that the extended surface is thin enough that we can neglect conduction in the transverse directions. So we only have conduction in kind of this primary X direction along the fin. And so that assumption basically says that we're taking each cross section to be at a uniform temperature along the fin. So in this situation, we now have convection up and down from the primary fin surface. So now we have conduction that is perpendicular to convection. And again, we have the surface is at temperature Ts, and the surface area is now this entire area, including the external surface area of the fin, rather than just the frontal area of the plane wall. So we've got an increased surface area here. Okay. So one aspect of extended surfaces, so typically you're trying to kind of increase the amount of heat that is being transferred by convection. So you want to, if you're going to go to the trouble of designing a fin, you want it to work as well as possible. And kind of by nature of the fact that you have convection heat loss along the fin, that's going to cause the temperature along the fin to drop. So you've got heat being lost continuously as you go down the X direction, and that's causing the heat or the energy at this point to be lower than the energy at this point. So you have a lower temperature as you go along the fin. So if you have a lower temperature at the tip, for instance, than at the base, you're going to end up with a lower delta T between the tip and the atmospheric temperature than at the base. So you have kind of decreased convection at the base than at the tip. So we can say the temperature decreases along the fin due to heat transfer by convection. Yeah.
And so for the fin or the extended surface, are we going to be considering the convection from the wall at all, or is it just kind of isolating the fin?
You're just isolating the fin, yeah. Yeah. So usually you use the wall just as a boundary condition, and it's like a set temperature. So we can draw this schematically. Let's take a side view of a fin now. We're going to have a certain temperature here at the base, T sub B. And then we'll have convection occurring along the length, but decreasing in magnitude as you approach the end of the fin. So we've got T infinity out here, T at the tip of the fin, convection occurring on both sides. And then we can say basically the temperature difference between the base of the fin and the atmosphere is going to be bigger than the temperature difference at the tip and the atmosphere. So that means that convection at the base is going to be larger than convection at the tip. So one way we can try to combat this is to use materials for fins that have higher thermal conductivities. So basically, if you have a material that conducts heat faster through it along the fin, then you'll have a higher temperature at the tip. Can you put it in the Dropbox? Thank you. Then you'll have a higher temperature along the fin, and at the tip of the fin than you would if you were using a material with a low thermal conductivity. So basically, the higher thermal conductivity enables the material to conduct heat, right, because we've got this heat being conducted this way. Conduct heat better along the length of the fin, and so you have kind of less of a temperature difference at the tip and between the tip and the base than you would with a material with a low thermal conductivity. So we can draw that out too. Let's see, so to combat the drop in temperature between base and tip, use a material with a high thermal conductivity. So let's look at a couple different circumstances here. So if we have a material with low thermal conductivity, let's draw a plot of the temperature distribution along the fin as a function of x. So down here we'll have our ambient temperature, and again this is assuming it's cooling. It's the typical application for fins. So the fin temperature is hotter than the ambient temperature. And then right here we'll have the temperature at the tip. And then the temperature at the base. So material with a low thermal conductivity looks something like this, qualitatively. This is not necessarily an exact shape, but you'll have some temperature drop between the base and the tip. Okay, if we have a higher K, and those of you who have already done the lab might have observed this with the different materials of the fins. Let's see. Didn't give myself much room here. But basically, if you have the same ambient temperature and the same base temperature, you'll end up with a similar distribution, but now the temperature at the tip is higher than it was previously for the previous material with low thermal conductivity. And then basically, kind of the best you can do to maximize heat transfer, which you can never actually achieve, you can just approximate, is having a material with an infinite thermal conductivity. And so if we had that, again, T infinity, and with an infinite thermal conductivity, there would be, theoretically, no loss between the base and the tip, no temperature difference between the base and the tip. So you would have kind of the same temperature throughout the entire fin. So because you're able to have a larger temperature difference across the entire fin with a higher thermal conductivity, that leads to enhanced convection. So you're maintaining a higher temperature difference, which increases convection. So as you increase the thermal conductivity, you have enhanced convection. Okay, so yeah.
You said the bigger temperature difference is what helps convection?
Yes. So if you're assuming that, sorry, the bigger temperature difference between the fin and the atmosphere.
Oh, okay.
Yeah. Yep. In your convection equation, you've always got a surface temperature and a fluid temperature. Yeah, so a higher surface temperature leads to a bigger difference between the two. Okay, so there are many different types of fins. You've probably seen some on like window air conditioning units. Those are the ones that like you always see like the handprint on, you know, people are like sticking their hands on the fins and like ruining all the heat transfer properties. And there's some pretty cool examples of fins in the heat transfer lab if you want to like take a look at some of them while you're doing the pin-fin experiment. But there are a few main types that we're going to consider. So we'll list them out, and then instead of drawing them, I'll just show you pictures of them from the book. They're somewhat complicated to draw in 3D. So types of fins. We have straight fins, which are extended rectangular surfaces attached to a plane wall. And these can have a uniform or a variable cross-section along their length. And I'll show you examples of both of those. And then the second type are pin fins, which technically in the lab, I believe we call it the pin fin lab, but I think there are 3 pin fins and 1 straight fin because it's a square cross section. So same thing except extended circular surfaces attached to a plane wall. Again, uniform or variable cross section. And then there are annular fins, which are a little bit harder to visualize, but I'll show you a picture. And they are circumferentially attached. Circumferentially attached to a plane wall. And so, by definition, their cross-sectional area will vary with distance from the cylinder. Sorry, these are attached to a cylinder. And the cross-sectional area varies with the distance from the base of the cylinder. And then the last type, oh, nope, that's it. Just those 3. Yeah.
Show us a sketch of an annular.
Yeah, definitely. I've got pictures right here. I didn't want to try and draw all of these. I don't think it would work very well. But yeah, I'll move this over. So this is a straight fin, right? So you've got a rectangular cross section similar to what we've been drawing before. Again, straight fin, it just has a non-uniform cross-sectional area. So here the cross-sectional area is the same as you go along the x-axis. Here the cross-sectional area varies from a rectangle, into, the whole shape is a triangle, but basically the rectangular cross-sectional area is just decreasing as you go along x. And then this is what an annular fin looks like. So you've got a cylinder and then kind of a circular piece coming out, and then the cross-sectional area is going to be what is basically the perimeter of the circle as you're going out, and that's going to increase with distance from the base of the cylinder here. And then this last one is a pin fin, and this one just is shown with a varying cross-sectional area, but like in the lab, you can also have uniform for a pin fin. So 3 main types, straight and pin fin, which both of those can have varying cross-sectional area, and then annular, which has a varying cross-sectional area by definition. Yes?
Can the annular one also with taper?
Yeah, I think that, there's plenty of different fin designs, and there's a section in the book that talks about specifically non-uniform cross-sectional areas. I think they have all kinds of crazy things where it like comes out in kind of like a triangle type thing. Yeah. Okay. Questions on this so far? All right, so the point of using fins, as we said, is to enhance the convection heat transfer. And we want to know, typically how well our fin is performing. So we need to be able to quantify what the convection rate is on a fin. And in order to do that, what we've done in the past is develop the equation for the temperature distribution in an object, take the derivative, and use that to calculate the heat transfer rate. Or that's one method of doing it. So what we need to come up with is an expression for the temperature distribution along a fin. And then that will allow us to calculate the heat transfer rate, Q sub F. So just heat transfer rate of the fin. That's all that F stands for. Okay, so last time, does anyone remember what we did to come up with the equation that would let us solve for the temperature distribution? Yeah, so we had a little differential element, a 3D little cube, and then we said we have some heat going into it and some heat going out of it, and applied a first law energy balance. So we're going to do a similar thing here, but there's one big distinction. So in the previous case, all we assumed was there was no bulk motion. So we're just saying we have energy coming into and out of this box, and it's being transferred via conduction only, but it doesn't have to be steady state. It doesn't have to, there can be energy generation. So the only assumption was that there was no convection within the element. We allowed there to be convection boundary conditions afterwards. So the big distinction here is that for a fin, we are going to go ahead and apply the assumptions that it is steady state, there is no energy generation, heat transfer is one-dimensional within the fin, the conduction is one-dimensional, and I believe we assume the material is isotropic as well to begin with. And kind of the main reason for doing that in this application, at least, is that the way we're going to be using fins is that's typically the case. And that making those simplifying assumptions allows us to derive analytical expressions for the temperature distribution. Okay. So let's draw a differential element of a fin. And then I'm going to state here all the assumptions that we're making. So we're assuming one-dimensional conduction. We're assuming steady-state operation, isotropic material, no energy generation, and then a new one that we've kind of been assuming implicitly but haven't specifically stated is that H, the convection heat transfer coefficient, is uniform over the entire surface. Yeah.
Is that a big assumption to make, or is that pretty accurate for?
I think for the kind of systems that we're looking at, just like simple straight fins, it's an okay assumption. So if you have basically what would cause the heat transfer coefficient to be, or some things that could cause it to be non-uniform are, it all depends on the boundary layer, right? So the surface finish, if you had like a pin that had a really varying surface finish over the entirety of it, if you have something where you have a really low thermal conductivity, so you have a much higher temperature at the base than at the tip, and you're going to have much kind of higher convection, just even like the flow that's associated with the free convection at the base could be different than at the tip and cause like maybe slightly different turbulence effects that are affecting the boundary layer. So generally it's a good assumption for kind of this simpler fins that we're going to be looking at. Yeah. And it is also kind of a big point to think about if you're looking at, like, say you have a plate and then a flow coming over it, and you're going to have some developing some like entry region where you have the boundary layers growing, and there will be a big difference between the heat transfer rates or the coefficients in the entry region and in the fully developed boundary layer too. Okay, so let's take our differential element, and I'm going to draw a rectangular differential element, but this derivation applies to all of the shapes that we discussed previously, because conduction is in one dimension along the length of the fin. The shape of the fin specifically doesn't matter. You just will, can still calculate the surface area and the cross-sectional area. So let's draw this nice and big. So this is just a rectangular element. And then again, we'll have conduction in and out. So Qx and Qx plus dx. We have the surface area, which, because this is a differential element, we're going to label dA sub s. So that's the area kind of on the outside, and then the cross-sectional area we're assuming it's we're not restricting it to be a uniform cross-sectional area at this point, so it's a sub c as a function of x. So the cross-sectional area can change with x. And then here, we're basically defining our x direction this way. And so again, we're assuming that the temperature on every cross-section is going to be uniform. And then we'll say this applies to all fin shapes discussed. And then lastly, and importantly, we're going to have some differential convection occurring outward from the surface. And that's D differential because it's occurring over a differential surface area. Okay, so we'll start with, so because of all of the assumptions that we made, our first law is simplified significantly, right? So we just are left with the energy in equals the energy out. And we'll look at it on a rate basis. So we'll say this is the first law with assumptions applied. Okay, so what all do we have coming in and what do we have going out? So looking at the schematic, we've got the only heat entering the system is Q sub x. And then leaving is Q sub x plus dx, and then this convection. So Q sub x equals Q sub x plus ds plus dq convection. And just like before, when we did the derivation for the heat diffusion equation, we're going to come up with expressions for each of these three terms based on things that we know. So the first thing that we know is Fourier's law, which allows us to come up with an expression for the conduction heat transfer. And here it's just negative k a sub c dt dx, and the a sub c is just to denote that we're talking about the cross-sectional area, just because now we have two areas, but it's the same area as before. And then just like last time when we wrote the expression for qx plus dx, we're going to say that's equal to q sub x plus the change in Q sub x with respect to x multiplied by the distance that we go in x. So this is the same expression that we used before for the heat diffusion equation for Qx plus dx. Okay. So, bring up a new page. Yes.
Did you say that there's a uniform temperature on every cross-section?
Yeah, that's what we're assuming.
That's just, but that temperature can change depending on where you're at?
Exactly.
Oh, okay. Just uniform across, I guess, like the cross-section of the fin?
Yep.
Okay.
Yeah. Yeah, so that assumption is because you assume the fin is thin and that the temperature is going to basically equilibrate across the cross-section very quickly. The fin is thin.
So there will be a dTdx. That's
Yes. Yeah.
okay.
Just no dt dy or dt dz.
Okay.
Yeah. So that's where the one-dimensional conduction comes from.
Yeah.
Yep. Okay, so now we have this expression for q sub x and q sub x plus dx. And then we basically plug this into here. So we'll plug it directly into here and then just take the derivative of it and multiply that by d sub x, or dx. So just Fourier's law, negative k ac dt dx, and then the derivative of that with respect to x multiplied by dx. Okay, so now let's handle our convection term. So we'll use the convection rate equation, Newton's law of cooling, and again we just have the derivative area, DAS. And this is basically written with the assumption that for a fin, you will always put your origin in the middle of the fin, which is pretty standard. So then, again, this is consistent with the negative of the delta t if you assume that the origin is in the middle, and then you have basically t2 minus t1 would be infinity minus surface, and the negative of that is surface minus infinity. So we can just write that to be clear. Origin in the middle of the fin. It's a little hard to draw sometimes. Okay, so now we have expressions for all three of these terms that are in the kind of original equation here. We plug them all in, and get this expression. And then we're going to expand it a little bit by evaluating this derivative. So we end up with the second derivative of the temperature with respect to x plus 1 over the cross-sectional area, the derivative of the cross-sectional area with respect to x dt dx, minus 1 over ac h over k, the derivative of the surface area with respect to x times the temperature difference T minus T infinity equals 0. So this is kind of the final form of the differential equation that we can use to solve for the temperature distribution within a fin. Unfortunately, there isn't really a name for this equation in the book, so we can just kind of say differential equation used to solve for the temperature distribution of a fin. And remember, the big distinction between this and what we've done previously with the heat diffusion equation is that we have already assumed one-dimensional conduction, steady state operation, no energy generation, and isotropic. Okay, questions? Yeah.
If you go back up to the top diagram, so this is for the convection from on the top side, or like on a differential on the surface?
It's the entire surface. Yeah, so this dq convection in the equation, we have, where'd that equation go? Oh, right here. We have dA sub s, so that's the entire differential surface area. Yeah. Did you have a question?
Nothing.
Okay. So again, just like before, this is a differential equation, and if we're given appropriate boundary conditions, it's steady state. We've already assumed it's steady state, so we won't need initial conditions for this case. Given appropriate boundary conditions, we can solve it for the temperature distribution in kind of fins of different geometries and different temperatures. Okay, a couple more things. The origin is at the center of the fin. Just reminders. You probably won't run into any situation where this isn't the case. Yeah.
Could you expand on that? Is it sort of the center of the cross-sectional area at the base of the fin, or is this at any cross-section? We put it at the center of whatever shape that is?
Yeah, so typically it'll be, the origin will be at the center of the fin at the base. For the discussion that we were having about basically the sign convention of the convection part of it, really what matters is how kind of like the y and the z are defined going outward. So it's just saying, yeah, but basically the center line. Yeah. And that's just to explain how we're writing this convection here.
Is this only convection in, I guess, this is for like net convection, I guess? Because if it's convecting from
Yeah.
both the top and bottom.
Yeah, so this is kind of a simplified figure. We can, I'll clarify this here on the figure. So this is a convection for the entire surface area of the differential element. So the entire surface area of this differential element here, and that's reflected in our equation. So the way we expressed this differential convection, this is the dA sub s, so that's the entire surface area of the differential element.
Like top and bottom?
And sides. Yeah.
So if it was an actual rectangle, we would be multiplying. We'd have to consider all faces, right?
Yeah, so the next thing we're going to do actually is solve this specifically for different shapes. And you'll see that the expressions for a sub s end up being like 2 times the width plus 2 times the thickness times the length. Yep.
Okay.
Okay. So then we can use this to, so basically apply boundary conditions, solve for specific temperature distribution, and then take the derivative and solve Fourier's law for the heat transfer rate. So that's kind of where we're headed with this. Any last questions? I think we'll stop here, and then on Friday we'll just derive the specific temperature distributions for different types of fins, and then that's where we'll get the equation that you see in your lab handout from. But kind of the important things that you need to know for the lab, we've already covered here, and that's basically that this equation and where the temperature distribution equation comes from is subject to all of these assumptions inherently.